Building a mathematical object with strict binary constraints often creates severe computational friction, and when you force millions of ones and negative ones into absolute orthogonal alignment, the structure usually fractures. A Hadamard matrix of order 668 is a 668 by 668 grid, where every entry is exactly +1 or -1. When this matrix is multiplied by its transpose, its reflection across the main diagonal, the result must equal exactly 668 times the identity matrix, a grid with ones on the main diagonal and zeros everywhere else. The global Hadamard conjecture posits that a matrix satisfying these strict conditions exists for every integer size that is a multiple of 4. The mathematician Jacques Hadamard established the foundational bounds for these matrices in 1893. Since then, mathematicians have mapped nearly the entire space of possible sizes, yet 12 specific matrix sizes up to order 2000 remain completely undiscovered. Order 668 is the absolute smallest of these missing matrices, and it has resisted every attempt at construction. Brute forcing the solution is impossible. A search space of this magnitude outpaces modern hardware entirely. Attempting to map the 668 matrix using quantum annealing frameworks would require over 15,000 logical qubits, far exceeding current capabilities. The difficulty in finding this matrix indicates a structural anomaly that evades known mathematics. To organize the search, we map the problem using a presheaf of constructions. This is a categorical framework detailing 19 distinct mathematical pathways, or stocks, historically used to build Hadamard matrices. Currently, 12 of these stocks are provably empty due to hard mathematical obstructions. The remaining 7 are categorized as unknowns, representing exponentially vast search spaces. To understand why order 668 remains unsolved, we must systematically walk through the math and sever those 12 empty stocks. This process of elimination will show that finding this matrix requires abandoning classical symmetry and standard algebraic tools. Classical construction methods rely heavily on the properties of finite fields and prime powers to generate orthogonal arrays. The recursive tensor product method, pioneered by James Joseph Sylvester in the 19th century, fails immediately. That method requires the matrix size to be a perfect power of 2, and 668 is not. The Paley type 1 construction targets matrix sizes where n-1 is a prime power. For our target, n-1 equals 667. Because 667 factors into 23 times 29, no finite field of that size can exist, completely neutralizing this approach. The Paley type 2 construction targets sizes where half of n-1 yields a prime power. For 668, this yields 333. While 333 passes the required modulo 4 congruence test, its prime factorization is 3 squared times 37. It fails the strict prime power test, breaking the construction. The Kronecker tensor method fails because 668 cannot factor into smaller known Hadamard orders, since 167 is odd. The Bush-type construction requires a perfect square, which 668 is not. The specific prime factorization of 668 and its adjacent integers systematically neutralizes over a century of number-theoretic constructions. With number theory exhausted, we look to group cohomology. This approach maps algebraic functions called 2 cocycles over specific structural groups to generate the matrix. There are exactly 4 unique algebraic groups of order 668, derived using Sylow subgroups. These consist of 2 cyclic and semidirect groups, plus 2 abelian and dihedral groups. Calculating the second cohomology group for the cyclic and semidirect structures yields exactly 2 cocycle classes each. Applying the Kunith formula to the remaining abelian and dihedral groups reveals exactly 8 cocycle classes for each. Researchers recently ran exhaustive computational checks on all 20 of these cocycle classes, testing both their developed and direct forms. Every single class fails the orthogonality requirement. The maximum off-diagonal inner products hit exactly 668 in every case, meaning the rows do not cancel each other out. The cocyclic mathematical route is completely closed. Any viable search is forced into the exponentially harder territory of circulant arrays. The search now relies on Williamson and Goethal-Seidel constructions. Both require finding 4 smaller 167 by 167 matrices, where each row is shifted by 1 position, known as circulant matrices. Attempting to use the natural automorphisms of the integers modulo 167 on symmetric pairs triggers an orbit collapse. This reduces the search space to just 256 uniform candidates, and every single one fails. A more complex algebraic approach attempts to build sequences from the span of the identity matrix and the Legendre quadratic residue matrix, represented here by the equation alpha I plus beta q. The rigorous addition required by the Williamson array forces the sum of the beta coefficients squared to equal 0. This completely annihilates the Legendre coefficients, leaving only trivial scalar matrices that cannot form a valid solution. Any valid solution is algebraically forced outside the standard quadratic residue subspace, breaking our most reliable symmetry tools. With algebraic paths blocked, computational mathematicians use heuristic gradient descent algorithms, often seeding them with Legendre sequences as a starting point. This chart shows the discrete Fourier transform power spectrum of the Legendre sequence. For all non-zero frequencies, it maintains a perfectly flat power output of 168. When 4 sequence copies are combined in the Goethel-Seidel array, the power output quadruples. 4 times 168 yields a power of 672 at non-zero frequencies, against a target output of 668. This creates an exact excess of 4 at all non-zero frequencies, and a massive deficit at frequency 0. The resulting sum of squared errors yields a total spectral defect of 443,552. This specific spectral profile acts as a massive topological ditch. It is a structural local minimum that permanently traps all greedy descent algorithms, preventing them from finding the true solution. Returning to the pre-sheaf, 12 stocks have been surgically severed by number theory, cohomology, and symmetry collapse. The remaining stocks are blocked by an integrality obstruction. The required spectral equations can be easily solved using continuous real numbers, but the strict constraint that every entry must be an integer, specifically positive or negative 1, shatters those solutions. For decades, mathematicians have deployed massive cluster computing resources to search these exact spaces using Turin-type sequences. The mathematical frontier for Turin sequences currently sits at length 44. Solving order 668 requires discovering length 56. Bridging that 12-step gap requires years of modern supercomputer time per single step. The remaining viable stocks require searching exponentially vast spaces where symmetry has been deliberately broken. Recent research explores new topological frameworks, like the Propus array construction. This method reduces the required independent circulant blocks from 4 down to 3, shrinking the search space to 2 to the power of 249. Another approach utilizes modular Golay quadruples. This method relaxes the strict mathematical rules, acting as a staircase to slowly approach the matrix using modular arithmetic. This visual represents the modular congruence plane. Supercomputers have successfully proven the relaxed condition, where the matrix product is congruent to 668 times the identity modulo m, but only up to a modulus of 64. A formal mathematical rule called Proposition 1.1 guarantees that if researchers can push the modulus m past 668, the modular solution is mathematically forced to lock into a true integer Hadamard matrix. Solving the 668 anomaly is not a matter of waiting for faster brute force computers. It requires discovering a new algebraic structure hidden deep within the remaining dark space of the pre-sheaf.